All right, welcome back, chemistry people. Are we ready for some more chemistry? We've got 3 problems on this video we're gonna work through. First 2, pretty short, pretty sweet. Last one, get comfortable. Question number 1 says, calculate the mass percent of each element in potassium ferrocyanide. Woo, awesome formula there. Pretty simple when you're working with mass percent or percentage in general. You need the part out of the whole times 100. And that will give you your percent, in this case, the mass percent of each element. So to start, we're going to take a look at the first element, which is potassium. Looking at the formula, we recognize that there are 3 potassiums. Each potassium has a mass of 39.10, which means combined, the 3 potassiums are giving us a total mass of 117.30 grams. Next, we've got iron. As we look, there's only 1 iron. The mass of that 1 iron is 55.85 grams per mole. So 55.85 or AMU. Our next element is carbon. Be careful here. It's within the parentheses there, and there's a little 6 outside. So there are 6 carbons times 12.01, again coming from our periodic table, which means the total mass of all the carbons are 72.06 grams. And then lastly, we've got nitrogen. Similar to carbon, there are 6 of them. The mass of the nitrogen, however, again coming from our periodic table, is 14.01, which gives us a total mass of 84.06 grams. So the total mass of all of the elements combined in this formula is, which means that the molar mass of potassium ferrocyanide is 329.27 grams per mole. We've just summed together all of these values. Awesome start, but this problem is asking for the percent of each element, the mass percent of each element. To solve for the mass percent of each element, all you need to do is take the mass of the part. In this case, the percent potassium is going to be 117.30 grams over the mass of the total, which is 329.27 grams, times 100, which will give us 35.62% potassium in this sample. The iron, percent iron, 55.85 of that 329.27 is iron, which works out to approximately 16.96% iron. Carbon, who's excited, are 72.06 grams of carbon in the 329.27 total. Works out to 21.88% carbon. And then finally with nitrogen, same deal. Percent nitrogen is equal to 84.06 out of our total 329.27 equals 25.53% nitrogen. Woo! As a quick check, you should make sure that these values, when you sum them together, equal 100%. If they don't, this one's going to add up to just under 100%. But again, it should be 100 or really, really close. The only time it doesn't is, due to some of the rounding that we did here with our percentages. So just check yourself before you wreck yourself. Woo! Next question. Okay, the analysis of a rocket fuel, some rocket fuel right now, showed that it contained 87.4% nitrogen and 12.6% hydrogen by weight. Mass spectral analysis showed the fuel to have a molar mass of 32.05 grams. Question number 2. What is the empirical formula of the fuel? Question number 3, what is the molecular formula of the fuel? Well, before we start this problem, anytime you're doing empirical formula calculations in which you're given percentages, always assume that you have 100 grams of your sample. You can assume whatever mass you want, but since we're working with percentages, 100 grams is the easiest because as we look to determine moles of each element we have, so we can write our empirical formula, it's going to be easiest with 100 grams. So as we take a look at nitrogen, again, assuming 100 grams, 87.4% of a 100 gram sample is going to be 87.4 grams. Super easy, right? We are going to quickly convert that to moles. Again, the 14.01 is coming from the periodic table, which means that if we had a 100 gram sample, 87.4 grams of it would be nitrogen, which means we would have about 6.24 moles of nitrogen in that sample. With hydrogen, very similarly, we would start with 12.6 grams. Again, just converting that percentage to grams by assuming 100. Our molar mass of hydrogen, 1.008 grams, again coming from the periodic table, which means that we're going to get 12.5 moles of hydrogen. Now, when we're trying to figure out the empirical formula, again, it's just a ratio of the moles. So as we compare these two, I mean, these are pretty easy numbers to work with, but if you're unsure, you always just divide by the smaller of the two. Which means that for every 1 mole of nitrogen, we're going to have approximately 2 moles of hydrogen. Therefore, our empirical formula is going to be NH2. Now, to determine what our molecular formula is, we're first going to figure out what the molar mass of our empirical formula is. And I'm going to roughly estimate 14 from the nitrogen plus 1 from each of the hydrogens, which means our molar mass is approximately 16 grams for this empirical formula of NH2. Now, as we take a look at the problem, we're told that the molar mass of the actual compound is 32.05 grams. So all we need to do is take that 32.05 grams, compare it to our roughly 16 grams from the empirical formula, which tells us that our molecular or actual formula is roughly 2 times larger than your empirical. Therefore, your molecular formula, molecular, is going to be twice as big, or N2H4. We just use this multiplier. We just use this multiplier and apply it to our subscripts to give us our molecular formula here, N2H4.